Welcome. Today we are going to talk about a technique called inspection, and specifically we'll look at analysis by inspection. I'm Vivek Subramanian.
I'm Michelle Maharbiz. Let's get going. So let's start by taking nodal analysis and seeing how we would do this by inspection. So before I even start, where is this coming from? If you maybe were paying close attention when we were doing nodal analysis, you might have noticed that however we put our equations together, the equations had a certain structure to them. And I pointed some things out. I said, oh, look, the sourcing terms are always on the right side of the equation once you factor out the node voltages. And the node voltages have these sort of terms to them. And it turns out that this structure can be used to look at a circuit and kind of reconstruct these equations without going through all the formal trouble of nodal analysis. So let me show you what we mean by this. Now, first of all, and this is really crucial because the biggest pitfall of doing this, and in some courses they omit this altogether, to be honest with you, the biggest pitfall is that if you don't follow the requirement very clearly for nodal analysis, and we'll give you the requirement for mesh analysis, you're going to apply this to a circuit which it doesn't work for. So all sources have to be independent current sources if you're going to do this. Now, that severely restricts the circuits you can do this on, okay?
So I assume, though, for example, if I had a circuit with independent voltage sources, I could just do a transform to make them into current sources and then apply nodal analysis by inspection.
That's absolutely true. But I want to make this very clear because, there's certainly dependent sources and other things you're not going to be able to do this on. You're going to make a big mistake if you do this. Okay, so let's assume that we've got a circuit that fulfills this. So what we're going to do is we're going to construct the equations required to solve for the node voltages. We're going to construct them literally by looking at the circuit and following some rules. We're not going to pick node voltages and then do KCL around each node voltage and then come up with these equations. We're going to essentially short circuit all of this because the equations, when you do nodal, always come out a certain way. They just always will. So we can kind of cheat and jump to the structure we know they will have. So what do I mean by that? When you do nodal, you always end up with a series of equations that in matrix form look like what's shown here. You're going to have a matrix which is representative of the conductances associated with that circuit. Now remember, conductance is the inverse of resistance. So if you're comfortable with the idea of resistance, 1 over R is going to give you G. And I'll be more explicit in a minute what I mean by conductances, and Vivek will work through very carefully an example, really sort of ad nauseum, to make sure you get it. But the basic thing is you're going to have a matrix which is conductance. If you think back to a nodal problem you may have already done, or one of our examples from earlier, you remember you get all these 1 over R terms before the voltages. And then these are the voltages you're solving for. This is this vector V, which consists of all the node voltages. You're solving, those are the unknowns. Equals, and then these are the source terms. And these have something to do with the current sources present in your circuit. So, well, go ahead, Vivek.
And I assume this is why we're using, we require that this only be used with independent current sources, because that's what allows us to get the right-hand side of this matrix equation.
That's right. Now, of course, if you do normal nodal analysis, you don't have that requirement, and you will get something of this fashion. You'll get something with this structure, but we can't guarantee that these G's follow the rules down here, and that these I's follow the rule I'm about to say. The point is, you'll always have this structure, but the cheating I'm going to do is I'm going to tell you what to fill into this matrix, and that only follows if you only have independent current sources. So if you only have independent current sources, then if you look at the conductance matrix, the diagonal, the components of the diagonal, so what do I mean by the diagonal? G11, G22, G33, and so on up to the last node, G, whatever that may be. If you have 7 nodes, it'll be G77. This is the diagonal. What goes into here is the sum of all conductances that are connected to that node. So if you have a node 1, you look at all the conductances that are connected to it. That's the inverse of the resistors. And you sum them up and you put them there. So don't worry if you don't quite visualizing this in your head. We're about to do an example in a lot of detail.
And we should point out as a reminder for you, those of you who haven't looked at matrices for a little while, the subscript in G11 means it's in the first row and the first column. So G21 would be in the second row and the first column, and so on and so forth.
That's all the subscript mean. There's the address in the matrix. Thanks. That's a good point. So now, the off diagonals, in other words, everything else, G12 and G34 and G76, whatever, those are going to be, you're going to fill those in with the negative value of the conductances connecting the two nodes that have the subscripts of the row and the column. So, for example, G21 here is filled in with the value of the negative of the conductance that connects node, say, 2 and node 1. So let's say between node 2 and node 1 in your circuit, you have a resistor of 3 ohms. So you would have a negative 1 over 3, because the conductance of a 3 ohm resistor is 1/3, and then you put a negative in front of it. Again, don't worry if this is all a little bewildering. We're going to go real slow in a minute with an actual example. The V's, as I said, they're just simply the unknowns. They're the node voltages that you always solve for in nodal analysis. And then I's, the I's for each row, the I for that row is the total current source, you add up all the current sources that are entering that node. Okay? And we'll show you that in a minute. So if you have a bunch of current sources going into a node, you add up all the values and you put it there. So
we should add one thing here.
Okay.
When we talk about these numbers, the sum of all conductances, or the negative of the conductances connecting nodes, etc., we're referring to direct connections. So when we say the negative of conductances connecting nodes K and L, that means resistors between K and L.
Physically wired up.
Right, not resistors going from K to J to Q to L.
Yeah, right. It's a lot. Don't overthink it. This is actually going to try to be very simple. And one thing to point out is that this is pretty much what computers do when they're deconstructing these types of problems. So let's see. Vivek's going to walk us through this circuit right here and follow all the rules I just gave you, and we'll go through it slowly.
So we have a circuit over here in the top left-hand side. And you'll notice, first, let's test to see if it meets the requirements. Requirements are, has to have only independent current sources. And sure enough, that's the case. It could have had voltage sources to begin with, but whatever happened, it's been transformed or what have you to come to a circuit that only has independent current sources. Therefore, it qualifies to meet the requirements for nodal analysis by inspection. All right. So I've set up the matrix that or the matrix equation framework that I'm going to populate, but I haven't populated it yet. So let's go ahead and get started. I'm going to start by doing the diagonal elements, namely the ones where the subscript numbers are the same, so the GKKs. And as a reminder, the rule for the GKKs is that they should be populated with the sum of all conductances connected to node K. So we have 4 nodes here, 1, 2, 3, and 4. So we'll have a 4 by 4 table. And let's go ahead and look at node 1. Okay? And we notice that there are 3 conductances connected to it. There's a 1 ohm resistor, there's a 10 ohm resistor, and a 5 ohm resistor. So we'll have 1 over 1 to get the conductance here, 1 over 5 to get the conductance here, and 1 over 10 to get the conductance here.
So one thing I want to point out that I've noticed people make a mistake on, it's not, you don't add up all the resistors and then take 1 over that to get some value. It's the sum of the conductances. So you have to take conductances first. In other words, every resistor has to be inverted, and then you add them up.
Right, and that's how you get to these numbers. Right. So you get 1 over 1 plus 1 over 5 plus 1 over 10, and that total is 1.3. So that's the G11 value. So we populate the first row, first column with 1.3. I can do the next one, G22. We'll do this again. So this is the second node, and we've got 1 over 5, 1 over 2, and 1 over 10. That gives us 0.8.
Right, let me do the third one.
Okay.
1 over 10, 1 over 20.
1 over 10, 1 over 20.
I'm so good at this, I could be a computer. How about the fourth one? 1 over 20, 1 over 10.
That's right. And so you see, you've now got all your diagonal values populated. Now let's move on to the off-diagonal points. Now the off-diagonal points, it turns out, have symmetry here. In other words, what that means is GKL will always be given the same value as GLK. And this is the negative of conductances connecting nodes K and L, with K not equal to L. Okay, so let's do one of those. So we'll start with the off-diagonal elements. And the first one I'm going to do is I'm going to pick nodes 1 and 3. And so that means I will get the values for G13 and G31. And I have a 10 ohm resistor. So the conductance is 1 over 10. And the negative of the conductance is minus 1 over 10. So I get minus 0.1. And that I populate G13 and G31 with those values. And let's do a few more. G12, I get minus 0.2 because I've got 1 over 5 and a minus sign, so I get minus 0.2 and minus 0.2. So remember again, G12 is between nodes 1 and 2, so I have a 5 ohm resistor. I can do G14. G14 is interesting because I have no connection.
There's no direct connection.
There's no direct connection.
You don't go around, like you said, you don't take a big loop that goes through another node.
Exactly. So the resistance here is infinite, which means the conductance is 0. So I populate those values with 0. G23, same thing. We get a 0. G24, I have a 10 ohm resistor, so I get minus 0.1. G34, I get a 20 ohm resistor, so I get minus 0.05. And at this point, I've populated the table in terms of the conductance values. Now I just need to figure out what's going on for the currents. So to do that, I remember my last rule, which is the ITKs are the total of the current sources entering node K. And the rule to remember in terms of the sign is a negative sign applies to a current source leaving the node in question.
All right, let me do the first one.
All right?
All right, so the first row is the current going into node 1. So that's 2 amps because of that 2 amp current source.
Exactly, and it is going in, so it's a positive.
Oh, all right.
And then the next one is we're doing it for node 2, and that's 3 amps because we have a 3 amp current source coming in. And then node 3, we have
4 amps coming in, but that means 4 has minus 4 amps because it's look at that.
There you are. 4 amps was leaving, so we get minus 4.
I'm so good at this, I could be a professor.
That's probably true.
Maybe true. It's not clear yet. Okay.
All right, so we've now populated the table, and now you get to, it's a straight matrix equation, which is relatively easy to solve, either using standard matrix manipulation, or you can plug it into your favorite numerical analysis tool.
So the thing to point out is, like you said, you can go solve this now. You're done with these system equations. If you'd done this by nodal, you'd have the same answer.
That's right. The equations you would get would have the same answer. The advantage of this is you didn't actually have to go and write the KCLs, etc.
That's right.
Having said that, there are few occasions where you would want to do this by hand. There's a certain pleasure in doing KCLs for yourself.
I suppose.
And so, this is mainly to show you the underlying matrix that develops and how this applies. It would basically be solved within a computer. And what you finally get is you can then solve the equations and you get the answers for the voltages. So we've calculated the node voltages without ever actually doing a KCL or a KVL.
Pretty cool. Okay, so you can also do this with mesh. And I don't think we need to belabor the point, so I'm just going to walk you through what are exactly analogous rules as for nodal. Again, there's a requirement, and just by symmetry you can imagine what that will be, that all the sources are independent voltage sources. Because what's going to happen is, again, by symmetry, your sort of forcing vector here is going to come from the independent voltage sources. You're again going to have a vector here that's an unknown, and these are now currents because it's mesh, right? Remember that in mesh we solve for the mesh currents. And this matrix, again by symmetry, instead of being conductances, will be resistances. Okay? And we're going to have very similar rules with the resistances as we did for the conductances in nodal. Now remember, you still have to kind of label these current meshes so that you know what to write, but just like you labeled your node voltages. But once you label your mesh currents, you can go ahead and work it through. So what I'm going to do is I'll give you the rules, walk you through them, and then for this circuit on the right and these 3 meshes, we've given you the answer. And I'll work out, or Vivek or I will kind of point out a few examples, and we'll leave it to you to confirm the whole thing, just to not be tedious, really. So, all right, so the diagonal members of the resistance matrix, they're going to be the sum of all the resistances in mesh K. So why don't we just go ahead and do it in real time. Let's take mesh 1. What are all the resistances in that mesh, so around that mesh? If I'm going around the mesh 1, so for R11, what are the sum of resistances? And let's go, you can already see the answer down here. There's a 2 ohm resistor. Let's say I start at the bottom left. This source doesn't count. 2 ohm resistor, 3 ohm resistor, 6 ohm resistor, and I'm finished. And in fact, 2 plus 3 plus 6. You can do the same thing for the second mesh, 3, 4, 5, and you see it here. And these are all the diagonal elements again for the other mesh, 5, 6, 7. They show up there. Okay? Now, the off-diagonal components, again, are symmetric, and they're going to be the negative of the sum of all the resistances. So you've got to get the resistances directly between those two nodes. You've got to take the sum and then take the negative.
And to be clear, this means, because we're talking about meshes now, we're talking about the resistances that are shared.
Oh, shared. I actually made that mistake. I said between those nodes. That's a good catch by Vivek. So I apologize. Let me be clear. The sum of the resistances shared between meshes K and L. So if, for example, I take mesh 1 and 2, what's shared between mesh 1 and 2? It's this 3 ohm resistor. So the negative of that 3 ohm resistor you see is -3, no problem. And again, if you look at 1 and 3, meshes 1 and 3, they share only the 6 ohm. So you get a -6 there and a -6 there. And if you look at mesh 2 and mesh 3, they have this 5 ohm resistor in common, -5, -5. So we're done. And now the forcing function part, or the part of the forcing vector. That's the total of all the independent voltage sources in the mesh, okay? With positive assigned to a voltage rise when going clockwise. All right, so let's take a look. If I start down here at the bottom left, like I like to do, I'm going to go clockwise, as stated by my rule. I rise by 6 volts, because I'm going from minus to plus, so I'm going up. It's like going uphill, so I'm rising by 6 volts. I keep going around, mesh 1. Oh, there's a 4 volt, but now I'm going down, right? I'm going from plus to minus. I'm going downhill. 6 minus 4, 2. And that's what you get here. There is no source here, no independent voltage source, so that's going to be 0. And for this one, again, I'm going uphill. You know, let's say I start here and go clockwise. I'm just running into this 4 volt source from minus to plus, and I get a 4 volt. And that's it. I mean, we've really kind of worked it out for you completely.
So what you've seen now is we've got an analogous system. You can solve this again by plugging it into your favorite numerical analysis tool to solve these. This is it as far as inspection is concerned. Inspection is we're using it primarily to show you how you get these cohesive systems of linear equations that can be solved using a matrix formulation. And this makes it very mechanical. It takes all the detailed analytical requirements out of KVLs and KCLs, but correspondingly it is much more limited in that there's severe restrictions placed on how the analysis is done. So we'll stop here. We'll see you next time.
Thanks, everybody.